Okay, last time we were taking a look at how to use a source transformation called voltage source splitting to create an opportunity to apply superposition to simplify a problem. That particular one was a non-series parallel network, or ladder network with a bridging resistor across it, to make that easier. And we're going to look at, in this segment, sort of an associated transformation called current source splitting. Okay, so the way that voltage source splitting worked was we basically split a voltage source into multiple, as many as we wanted, replica sources connected in parallel, and then we cut the wires that were joining them. And so in this case, generically we might have some circuit here with some nodes in it. I'll draw these nodes, whatever. With some stuff connected to them. And there'll be a node here. Let's call this A, B, and C. And we've got some current source that's connected between nodes A and B. Let's say I in. And so the way that current source splitting works is I take this one source I in and I connect in series with it some number of replica sources that all have the same value. In this case, I'm just going to make it 2. And as far as the circuit is concerned, we still have the same situation. We have I in going into node A. We have I in coming out of node B. Really, that hasn't changed. So KCL is, every KCL equation in here is the same as it was. One thing, if you think about this a little bit, that's a little potentially disturbing. What is the voltage on this node between the two current sources that we've connected? I mean, KCL will apply, right, and be satisfied because we're pushing I in and sinking I out, so the sum of the currents in is equal to the sum of the currents out. And that's regardless of what the voltage is on that intermediate node. It could literally be anything. Remember, because these are ideal sources, and these ideal sources maintain the rate of flow of charge that's specified by the source value, regardless of the voltage across the two terminals. And so the voltage on this node can literally be any number, any real number. And KCL will be satisfied. And that means that this node is, the voltage on that node is indeterminate. We can look at that as a problem because, oh my gosh, we don't know how to find it. Or we can look at it as an opportunity. So we can say, well, if any voltage on this node is consistent with the circuit, then I can make this node voltage anything I like. And in particular, what if I want to make it the same voltage as some other node in the circuit? I'll just connect node C here to that intermediate node, and then whatever the voltage is on node C is the voltage on that intermediate node. Now, that may strike you as being an illegitimate thing to do, but if I ask, have I changed the KCL equation here at node C? The answer is no, I haven't, right? Because before, I had no current contributed by that node here, right? Whatever current was flowing in is equal to the current flowing out. And here, because KCL was satisfied at this indeterminate node, it contributes no current here. If you like, we're adding and subtracting I in. And that means that we haven't changed the KCL equation for node C. If you like, if you think of it as taking the old KCL equation that we had for node C, and we're adding I in to both sides of the equation. If we conceive of KCL as the sum of the currents flowing in is equal to the sum of the currents flowing out, because we have a current flowing in, which is I in from the source below, and we have current flowing out, which is also I in, which is the current flowing out from above. And so we don't change any of the KCL equations for the circuit, and that basically means that we haven't changed the solution to those equations, and so this is an equivalent circuit. Okay? And so what this will allow us to do is to, again, apply superposition. We can, if this is a linear circuit that we're applying this transformation to, then we can apply superposition and turn each of these replica sources, we can turn all of them except for one of them off at a time, and then sequentially go through and solve the circuit for each replica source, whatever variable we want to solve for, and then superpose the results. And that will often make our lives much easier. So my favorite example for this particular application of this transformation is kind of one of these brain teaser problems. So suppose we have an infinite rectangular mesh of resistors connected like something like this. Right, these are all R's, R, 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 and it just goes on and on forever. And suppose I take two leads out of here, move this R over here. I've got two wires on adjacent nodes here, neighboring nodes, and I want to know what is the resistance seen looking into that port. Now we haven't talked about this concept, but this is basically like if I took a multimeter and put it in ohms mode, and I put the plus lead here and the minus lead here, what would I measure? Okay. This is called a driving point resistance. It's one of the types of transfer functions. So there are basically 6 types of transfer functions, four combinations of current and voltage, where you have current or voltage as the input, or current or voltage as the output. You can get a voltage gain, which is voltage input, voltage output. You can get a current gain, which is current input, current output. And then when we talked about the dependent sources, you could have something called a transconductance gain, which is when you have a voltage input and a current output. So that has the units of mhos, or amps per volt, for the gain. You can also have a trans resistance gain, which is a current to voltage transfer characteristic, where you have current in and voltage out. So those are four possibilities, but there's an extra 2. When when you have a mixture of voltage and current at the same location. So it's not a transfer characteristic in the same sense as you have an input and an output at different places in the circuit, but you're driving a current into, let's say, 2 wires in the circuit, which is a port, and the response of the circuit is the voltage that develops at that same point across that same port. Okay, and that's what this driving point resistance is. So a driving point transfer function, input and output are at the same place. And Rn is basically a Vn over an In, and this is the response, and this is the stimulus. So the thing in the denominator is the input, and the thing in the numerator is the output in an arrangement like this. So this is the output, and this is the input. You can also have a driving point conductance, which would be a Gin, where you flip this upside down, and technically speaking, the voltage becomes the input, and the current becomes the output, the stimulus and the response. And in practice, these two things are basically just reciprocals of each other, and so you can actually excite the circuit in any way that's convenient for you. But for certain purposes, it's important to bear in mind that if you're talking about a driving point resistance, the actual stimulus is a current, and the actual response is the voltage, even if you may want to compute it the other way around. And in that case, you're dealing formally with a driving point conductance transfer characteristic. And this is, in fact, how your multimeter actually works. So usually there's like a little, let's say, 100 microamp current source that's well calibrated inside your multimeter. And if you put it in ohms mode, it basically sources that 1/10 of a milliamp current out of its positive lead. And that creates some voltage drop across the leads, depending on what you hook it up to. And then it basically uses its voltage measurement capabilities to measure the voltage across the 2 wires, and then just divides the 2 things and prints out the display what the resulting resistance is. All right, so what we're going to do to find this driving point resistance is to basically put a current source here, In, and we want to know what is the voltage that develops across those, and we're going to take Rin to be Vn divided by In. Okay, but it's not clear how to do this, right? Because we have an infinite network, and so if you wanted to apply nodal analysis, you'd have this problem where you'd have an infinite number of equations that you would need to consider. And so it's not even clear how to write down the nodal equations if you wanted to apply the method of last resort, which I wouldn't recommend. So what we're going to do instead is apply current source splitting and superposition. And I think you'll agree after we do that this is actually quite an easy problem. Okay, so we're going to replace that voltage source, or rather that current source, with 2 replica sources, In and In, and we'll call this source 1, we'll call this source 2. And what we're going to do is we can connect this voltage in the middle node to anything that's convenient. So we're just going to put it at ground. Okay. I haven't labeled any particular node here ground. Actually, officially what we're going to do is consider the voltage at infinity ground. Okay, so whatever those nodes that are infinitely far away is we're going to take that potential to be ground. and we're going to connect this node up to whatever that potential is. You can think of the Earth as being underneath this network, and we're just connecting it to the Earth. Okay, so we're going to turn off current source 2 by replacing it with an open. Like so. And we're going to consider, so Vn, or rather, yeah, Vn is equal to Vn1 plus Vn2. That'll be the superposition of the two components. This is the component of Vn due to replica source 1, In1, and this is the component of Vn due to the second replica In. Okay? And so we need to think about what this does. So we're injecting In onto this node. Okay, and this node is just open. Well, what happens? Well, this current comes down here onto this network, In, and it sees 4 places it can go. So the question is, how is it going to split? And now if we were in the same room here, I would probably pause at this point and ask you guys to think about that. And so I'll give you a minute to think about that. Or maybe you could hit the pause button and think about it. Well, this network is perfectly symmetric. It's infinite in all directions, and it's made of the same value resistors. So by symmetry, it has to split into 4 equal pieces. So In over 4 goes each of these 4 directions. Okay? Now, in particular, the voltage we want to know is this voltage here across this resistor in the middle. And we know the current flowing through it. So we can calculate Vn simply by Ohm's law, knowing that the current split into 4 equal pieces, and that one of those pieces is across this resistor. We can say that Vn1 is equal to In over 4 times R. And that's it. So now we move on to replica source number 2. So we open up replica source 1, put replica source 2 back on. Like so. And what we're doing is we're pulling In out of this node, which is the next node over from where we were injecting before. And that current has to come from somewhere. It comes from 4 resistors. And again, it's a perfectly symmetric situation. Right? So a fourth of it has to come from here. A fourth of it has to come from here. A fourth of it has to come from here. And a fourth of it has to come from here. And if the idea of pulling current out and having the current assemble from 4 pieces is difficult, you could imagine saying that this is the same as injecting minus In onto the node, and then considering how that minus In current splits where it goes instead of where it comes from. So that's another way of thinking about it. But Vn2 we can get in the same way. We know the current flowing through this particular resistor here, and it happens to be the same current and flowing in the same direction as it was before. So this is also In over 4 times R. And so Vn total is just In over 4 times R plus In over 4 times R. We can factor out the, well actually we can just combine them, right? They're the same. So it's going to be In times R over 2 we get 1/4 plus 1/4 is 2/4, or 1/2. And then Vn over In, we just move the In downstairs here, so Rn equals Vn over In, which is equal to R over 2. Pretty easy. Now, you may have seen a problem like this, and if you change this problem slightly, where let's say you want to know the voltage, let's say across a diagonal here between two nodes in a diagonal, well, then it's not quite so easy. So there are ways of solving that, but this particular trick doesn't work nearly as well. And I'll leave you to ponder that if you care to. So that's an example of current source splitting and superposition. I find myself using voltage source splitting usually more than I've used current source splitting. I tend to use current source splitting when I'm dealing with a situation where I need to, when I'm dealing with a floating node, or like a floating port where I don't have ground on either side, and I need to look at, let's say, the resistance seen looking into that port or something like that, like in this situation. I tend to use voltage source splitting when one side of the port is connected to ground, and I'm need to look at the voltage transfer characteristic, or even the resistance seen looking into the port, or the driving point resistance of that port. In that particular case, I'm probing it using the driving point conductance and then taking the reciprocal. As I mentioned, is something we can do as a matter of convenience if we need to.